Namaste and welcome back to JEE Chemistry with Typical Monk. This is class 36, Coordination Compounds. A coordination compound is a small architecture built around a metal, a central metal ion that accepts lone pairs from a ring of surrounding ligands, holding them in a precise geometry. The number of donor atoms is the coordination number. 6 gives an octahedron. 4 gives a tetrahedron or a square. Werner first explained that two kinds of valency. The crystal field theory then revealed why they glow with color, as the ligands split the metal's d orbitals into a lower and an upper set, separated by an energy gap that decides color and magnetism alike, from hemoglobin to chlorophyll. These complexes run the chemistry of life. Today, the complex, its geometry, isomerism, and bonding, one idea at a time. Here is what you will master today. First, the central atom, ligands, and coordination number. Second, Werner's theory and nomenclature. Third, isomerism. Fourth, valence bond theory. And fifth, crystal field theory, one idea at a time. Let us set the foundation. A coordination compound, a central metal bonded to surrounding ligands. The ligand, an ion or molecule that donates a lone pair to the metal. The coordination number, the number of donor atoms bonded to the metal. Master line, the metal accepts lone pairs, the ligands donate them. Now, look at the picture, a coordination complex. The central metal M, it accepts lone pairs from the ligands. The ligands L, each donates a lone pair to form a coordinate bond. Coordination number 6. 6 ligands give an octahedral shape. 4 ligands, they give a tetrahedron or a square planar complex. Now the key terms. Ligands, monodentate, bidentate, or polydentate by the number of donor atoms. The chelate, a ring formed when a bidentate or polydentate ligand grips the metal. The coordination number, 6 gives octahedral, 4 gives tetrahedral or square planar. The oxidation state, the charge on the metal, written in Roman numerals. Now Werner's theory and naming. Werner's theory. Primary valency is ionizable. Secondary valency is the coordination number. The naming order. Ligands first, alphabetically, then the metal. The oxidation state, in Roman numerals, in brackets, after the metal. Anionic complex. The metal takes the suffix 8. Ligand prefix says D entry or bis entries for complex ligand names. Now look at the picture. Crystal field splitting. The free ion, the 5d orbitals have equal energy. They are degenerate. The ligand split them into a lower T2 set of 3 and a higher Eg set of 2. The gap, delta, the crystal field splitting energy. It decides the color and whether the complex is high or low spin. Now, how the bonding is explained. Valence bond theory. The metal hybridizes its orbitals to bond the ligands. Inner against outer orbital. The d orbitals used inside or outside the valence shell. Crystal field theory. The ligands split the d orbitals in energy. High spin against low spin. A weak field keeps electrons apart, a strong field pairs them. The splitting explains the color and the magnetism. Now, the isomerism. Structural, ionization, linkage, coordination, and hydrate isomers. Geometrical, cis and trans, in square planar and octahedral complexes. Optical, non-superimposable mirror images. Now match each term to its meaning. A central metal plus ligands goes to a complex. The number of donor atoms goes to the coordination number. A weak field ligand goes to high spin. And d orbital splitting goes to crystal field theory. 4 pairs, each worth memorizing. Now, how many of these statements are correct? Statement 1. A ligand donates a lone pair to the metal. Correct. Statement 2. The coordination number is the charge on the metal. Wrong, that is the oxidation state. Statement 3. A strong field gives a low spin complex. Correct. So the answer 2 are correct. statements 1 and 3. The trap is the coordination number in statement 2. Now, the two mistakes that quietly cost marks. The truth, the coordination number counts donor atoms, not ligands. The trap, confusing the oxidation state with the coordination number. The second truth, a bidentate ligand occupies two coordination sites. The second trap, forgetting that strong field ligands pair the electrons, giving low spin. Now test yourself. Answer in your head before the reveal. That is how G-speed is built. Here we go. Question 1. What does a ligand donate? A lone pair. Question 2. The coordination number of an octahedral complex? Question 3. The charge on the metal? The oxidation state. Question 4. A ligand with two donor atoms? Bidentate. And question 5. A strong field, high or low spin? Low spin. Let us gather it all in one breath. A complex, a central metal plus its ligands. The coordination number equals donor atoms. The oxidation state equals the metal charge. Werner, primary, that is ionizable, and secondary, that is fixed, valences. Isomerism, structural and stereo. Crystal field theory, the D-splitting explains color and magnetism. Next class, the D and F block elements. Architecture around a metal. A coordination compound is chemistry as architecture. A center metal ion at the heart, ringed by ligands that each offer a lone pair and lock into a definite shape. 6 into an octahedron, 4 into a tetrahedron or a square. Count the donor atoms for the coordination number. Read the metal's chart as its oxidation state, and never confuse the two. Werner explained the two valences. Valence bond theory built the shapes from hybrid orbitals, and crystal field theory revealed the secret of their color, splitting the d orbitals into a lower and an upper set whose gap decides both the hue and the magnetism. From the iron in hemoglobin to the magnesium in chlorophyll, these are the molecules that color and power the living world. Next class, the D and F block elements. Sarah, David, Lisa, and John all began exactly where you are sitting now. One idea at a time, you will crack G. I will see you in the next class.